I want to do an example with you, okay, and so that we get used to doing and solving the problems. Okay. As you can read, this is a somewhat simulated problem. Okay, it's not actual problem, but let me also tell that it is not very far from the reality. Okay, but we have to say it is a simulated example. I'll show you a picture of the area Agra Mathura region in figure 1. Assume that the wind direction from the Mathura refinery, because we have talked so much in the country that emissions coming from Mathura refinery and affecting the Taj Mahal, right. Okay, so we will try to do some example on that. Assuming that the wind direction from Mathura refinery is directly towards Taj Mahal, that is generally true. Okay, that is generally true. The most of the time wind blows from Mathura refinery towards Agra. Okay. Upwind of the Taj Mahal, there are industrial areas and a national highway which passes very close to the Taj Mahal. Emissions and meteorological details of these sources are shown in figure 1 under the atmospheric condition E. Okay. What is E? What condition is E? Stable. Okay. And F was highly stable. Okay. Under this condition E, estimate the following in the vicinity of Taj Mahal at the ground level: SO2 concentration contributed by Mathura refinery, SO2 concentration contributed by each of the two industrial areas, and SO2 concentration contributed by the national highway. Okay. And you see these are very thing which you are very familiar with. Okay. So let's see if I can show you the figure 1. Okay. This is all the information which you all understand very well. Okay. So if the way I have the things here, let's go to picture 2. Okay. See, for the highways, how we do, this formula is given to you. The area source, what is to be done, that is also specified, that we have covered in the class. The area source can be an effective point source. Modeling will proceed as it would for a point source located at the center of the area, but with the initial crosswind spread, that is sigma y, in terms of the dispersion parameter sigma y as 0.25. Okay, you remember we said that was sigma y was the distance of the area source divided by 4.2. For that you can take as 0.25. Okay, where the y is the approximate crosswind extent of the source. Based on this, distance of the virtual point source from the actual source x naught may be calculated, that we discussed, right. Okay. Now what is the problem, what we want to say? Under the given conditions of emissions and meteorology, will the ambient air quality standard of 30 micron per meter cube be met at Taj Mahal? Okay. Use the attached tables that I will show you in a moment. And finally, what we want to do? We want to do some solution. Okay. We just don't want to stop saying, well, there is a problem or there is not a problem. Then finally, if you are not meeting the standard, devise a realistic scenario in terms of pollution control strategy which would result in adherence to the air quality standard, which will attain the air quality standard. So that the idea is to make what safe? To make Taj Mahal safe, right. Okay. Calculate the ambient SO2 concentration near Taj Mahal under the proposed scenario. Okay. You want to change the things, and after having changed the things, what would be the picture look like? Okay. Okay. Picture is not to the scale, of course, you can see. The picture you see here is, suppose this is the Taj Mahal you have, okay, and this is somewhere here is Mathura refinery. Okay. The aerial distance between Mathura refinery and almost up to Agra Taj Mahal is how much? 37 kilometers. and the details of the Mathura refinery emissions are the following. Okay. SO2 emissions 900 kg per hour. Okay. H is 100 meters. T stack is 220, T ambient is 20. I have already given you the speed at the height 100 meters. Okay. If it was not given to you 100 meters, you will use u1 by u2 equals to z1 by z2 to the power n, and where n is function of stability. Okay. That is already given. The diameter is given to as 2.5, the exit velocity is given as 12, and the atmospheric pressure is 1000 MB, and we have to find out the impact of refinery onto Taj Mahal. Okay. That is the idea number 1. Second thing, you have the two sources. Okay. The center of the source is almost, you see this is the, what are we saying as the source, area source 1. SO2 emission is how much? 100 kg per hour. Okay. All right. And H, okay, that is effective strike height is 30 meters. The wind speed is 4 meters per second. Okay. And then here this length was, does it show anywhere, but anyway this is 500 meters as you say. There is another source which is also 500 meters in the size. Okay. And this is located at some 4 kilometers, and this is located at 3 kilometers. And what you see here is a national highway which is going like this. Okay. And details of the national highways, the emission rate is 2.21 10 to the power minus 2 grams per second per meter, as you remember the units that will be. So H equals to 0, we are assuming that the plume rise from the vehicles is 0, okay, and phi is 90 degree. As you see the wind is like this angle is 90 degree, and this distance from the highway to Taj Mahal is 1 kilometers. Okay. This is the situation we have. So in air pollution what we do, from the various sources, okay, you find out the concentration, and simple summation of the concentration is the net impact, unlike water conditions. Okay. Water, what you consider the concentration, but you also consider the volume of the water that is being mixed. Here what we are saying, everything is being mixed, but then everything is a meter cube concentration per meter cube, and meter cube is the same. Okay. So this is what you have to do. So if you, we can start from anything, but let us start from refinery. So what is the condition we have? Stability is given to us as stability E. Okay. Okay, let me ask you, if suppose the day is very heavily overcast, okay, what stability you think it will be? Lots of clouds, and of course the wind speed is moderate kind of thing, 3-4. When you have lots of cloud, the normal stability you take is about D, okay, the neutral conditions. Okay. The stability is E. All right. Then what do I do? First of all, suppose we start with the Mathura refinery. Okay. Then I find out the delta H. Okay. What was that? Vs d by u at what number? 100 meters. Okay. U at 100. What was that? 1.5 P times Ts minus Ta by Ta into d. Don't forget that there is a diameter term also here. Okay. If you have the calculator, because I could not do the calculations, if you have the calculator, if you want to do very quickly, or if you don't have, you can take my calculator. So let's put the numbers here quickly. What is the Vs? 12. The diameter of the stack, keep telling me. 2.5. The wind speed at 100 meters, 6, 1.5, 2.68, 10 to the power minus 3 times, what is the pressure? 1000 MB, and then the other thing is TS, T stack is 220, 220 plus 273, okay. So that makes 493 minus 225 plus 278, 298. T stack, this should be T stack. (493) times the diameter, that is 2.5. Something like that. 20.75. Okay. All right. No question of aerodynamic downwash in this case. You remember the aerodynamic downwash we talked about? When the speed is high here, 12, and the horizontal wind is 6, do you expect any aerodynamic downwash? We don't expect, because the ratio of Vs to U is much more than 1.5. Otherwise, if that was the case, we will correct the height for aerodynamic downwash. Okay. So, the next thing you can write, this was our delta H. Okay. We generally correct this delta H for stability, right. We take this as 0.9 in case of the conditions are stable, right. For neutral, we take it as it is. Okay. So, then in that case, let us say if I multiplied with 0.9, the correction for stability, and let us say approximately this is 20, okay, meters. Okay. All right. I'll write the formula directly. Okay. What was that? Q upon 2 was 2 there. If I am now, I have to put what I have to find out. I have to find out y equals to 0 in this case. My x direction is always the wind direction. So, this is my x direction. Okay. So, what is y at this point? 0. What about z? 0. Okay. So, if you recall, from my general formula, 2 will disappear. Okay. Many times the student makes the mistake and carry this 2 forward. Okay. Because putting that equal to 0, and then there will be the 2 will come, because e to the power 0 plus e to the power 0 will be equal to 2. Okay. So, now you say pi sigma y sigma z. Okay. Now, what u should I take at height of h plus delta h. So, height of 120 meters, right. What is my h finally? Effective strike height is 100 is the, where is it, 100 plus 20. So, this u will be at 20, it will be at 120. So, just to save some time, we will take this equals to the number what we have, 6, okay. Because you see, as we go higher, it stabilizes, right. So, I will take this as, just to save time, I will take this as, the u I will take as 6 only, but ideally you should correct it.
In that case, what should be the n?
N value which we gave in the table last time to you, and you do not have to remember the n values. Okay. You can refer it to the book, or there is a question in the exam, it should be given to you, because numbers no one can remember. Okay. But you can modify the u if you like. So, let us continue to have the figure here. Exponential minus h square So Q, I should be careful with the units. So 900. Okay, I want to find out in micrograms per meter cube. So 900 times 1000 is my grams, right? Micrograms 10 to the power 6 pi sigma y and sigma z will write in a moment, 6 exponential, okay, and this we have to find out per second, okay, that is per hour. So, and my h equals to minus 120 square by 2 sigma z square, okay. So let's look for sigma y and sigma z. Okay, is there anything else I need? I don't need anything else. Okay. That is what is my sigma y. Okay. May not be very bright for you, but I'll try to read for you from here. Here is, okay, the distance in, oh, just a second, distance in meters, okay. Okay. So this is, how much is this? 10 to the power 3, okay. This is 10 to the power 4, right. So what is distance is this one? What is this distance here? 10 kilometers, right. Okay, and this is 100, right. 30, 37, go here, E here, okay. Okay, and this value, this is how much? About 1000, is it? We will take that as 1000. Okay, that's about, you can say about 1000, yeah. Oh, I'll take 1200 or so. Okay, 1200. Okay, so sigma y is 1200. Okay, sigma z, same thing. How much is that? 37. Stability E, 120, okay, 140. Can you please give me C, because of the Mathura refinery caused onto the So we immediately compare this with 30, then you obviously say, well, even the Mathura refinery is contributing much more than what is acceptable level at Taj Mahal. Because what was acceptable level, you recall? 30 micrograms. So this will keep at somewhere as our point number 1. Okay. So let's remove this area source. Okay, let's take the area source number 1. Okay, what is the quantity of the emission? 100 kg per hour. Okay. At this side, it's given is 500 meters. So sigma y naught 500 by 4. Okay. How much that comes out to be? 125. Find out x naught. Correct. Go back to the, what is that we want? This was 125. this is 10, this is 100, right? Correct? This is your 200, 125 is here, right? Go back here and somewhere here, right? And then come here. What is this coming out to be approximately? 250? Okay, I'll just check with this figure which is like accurate to me. What is that? Sigma y is your 125. Okay, you move here 125 and well, it is, well, I'm nearly getting 300 or so. Okay, right? Okay, you get 300. I think should it be 3 kilometers or 3 this thing? Fortunately, the picture, huh? It has to be 3 kilometers. So this is actually 10 to the power 3. Okay, it can't be such small. It's just experience which tells you. Okay. So now what is your, and this is your Taj Mahal somewhere here. So this distance is 300 meters. And what is this distance from center to this? 4 kilometers. Okay. 4,000 meters. So your x equals to really 4 plus 3, 7,000 meters. So the sigma y spread by the time it goes to Taj Mahal will be equal to, I have to find out the 7 kilometers. Okay. Take this, right? All agreed? This is your 2, 3, 4, 5, 6, 7. $300. Okay. On sigma z. Start from 5, 6, 7. F. Go back. How much?
6,000.
No. 60. 60 or so. 1, 10, 100. So I am here somewhere here. So 650 or something, right? Okay. And how can you quickly calculate the concentration? Oh, okay, all right. I agree with you. What was the H? 30 meters, and U30 is given to you as 4 meters per second. So you apply the same formula, identical to what we did for the Mathura refinery. Okay, how much that comes out to be? That was area source 1. So I remove this. I'll take the number you gave me. Okay. Now we have to do the same thing for source number, area source 2. Okay. So if you want to either quickly do that one, or we assume, okay, just to help to save the time, okay, you know how to do it for the area source 2, right? Okay. I can assume this to be nearly the 50% of source 1, because concentration is always proportional to Q. Okay. H is more or less the same, and what is the difference you will see is the difference of 1 kilometer distance, right? Okay. That will have the some impact, but then if we kind of agree for the saving the time, we can say it's 50% of area source 1, okay, because Q is 50%. So, this is for this area source 1, C for area source 2, that came out, that we assume that to be all right. Okay. Now comes to the national highway business. But let us keep writing somewhere here so we don't forget. Refinery, that is about 57, and then area source 1, that was about 100, whatever, 101 or something, 102. This is about 50. Not talk about the highway business. Source is your national highway. C was, what is that, 2 Q 2 pi something like this, and of course sin phi is 1. This will be my 2 times, what is a Q? 2.21 10 to the power 10 to the power minus 2. U we will take the same as 4 meters per second, and sigma z we must find out how far it is from the 1 kilometer. Okay. So, distance is take this, okay, 22 or so. This in grams, I want in micrograms. 10 to the power. Let's see what number you get. 200. See, I'm going by what numbers you are giving me, really. Line source. Most of you have got this 102, right? You have accounted for the microgram per second emission rate. Okay, okay. Then we'll assume that all thing is fine. Okay. So, what do you want to say? Well, there is a serious problem. I mean, it is a hypothetical case, more for learning. Okay, the situation may be very different on the ground, but then you say what you need to say. Well, every source needs to be controlled. Okay. So now what you do? The net concentration is okay. So what it tells you is, well, of course, the Mathura refinery is causing problem, okay, but then again the larger problem comes from the national highway, okay, which may be true also in some cases. Okay. So what are your options you have? What is that you can do? Close the refinery. Okay, but that is of no use at all.
First we know the characteristic of a wind. If it is
See, this is the situation we have. We are just talking about this situation. Okay, whatever the calculations we have done, we are talking about this situation only.
in case we have done some plantation like that, that's why they have developed a boundary here.
See, that again will not help much. Okay, because this thing you can't bring it down to 300 with the artificial means. So immediately you should think as a planner, as an engineer, is to realign the national highway, make an outer ring road or something like this. Okay, many of you are civil engineers, so you have to think, because you see here, no matter how good you bring the cars and how good you bring the trucks, okay, the emission is not going to be zero. Okay, so one of the solutions that you would immediately think is to get rid of the source. Okay, ask this whatever. Okay, these are just the options that you think of. Okay, and final decisions are taken with other considerations and what you can do and what you cannot do. But then of course, suppose this highway going like this, suppose it goes something like this, already in the downwind of this one. Okay, then automatically the contribution is zero from there, right? I am not saying this is the final answer, but we still have to make some sense from our example, which is, of course, we just make it for our learning. Okay, the realistic thing will be different, realistic models will be different. We can use more complicated models. Yeah, okay. Either you have the experimental results here, okay, but then you cannot say with the measurement alone that it is contributed by this or that. That you cannot say. It is only model, to some extent it can give you who is contributing to what extent. Okay. So one of the other ways to do is to use a tracer gas. Okay. Along with the emissions here, you release a tracer gas, okay, from refinery. Okay. And then you say here, and you release another tracer gas, okay, or the tracer gas at some other time from these things. Okay. And they measure the tracer gas, because tracer gas will not be contributed by anybody else. So then you can really establish, okay, as to how much is the contribution really in the measurement terms. Okay. Then you can take the ratio of the emission of this thing to the ratio of the tracer gas, and that same ratio will be maintained more or less as it travels through. Okay. Then you can find out how much is the contribution in realistic term from the Mathura refinery. Okay. So one thing which immediately one would think, provided these numbers are correct, these numbers you have given to me. So I would think, well, the alignment of the highway should be done. Okay. If we can do something about this thing, that emission is brought down, convert the processes here, we are using the coal and oil with more like CNG. Okay. Sulfur content in CNG is zero. Okay. The moment you say, all right, you are mostly because sulfur dioxide will come from the combustion processes, you say you use CNG. Okay. If you make them CNG or 50% change them to CNG, this is gone, and you ask Mathura refinery to control the emissions to, let's say, 1/3 or something. Okay. Because, and in fact, this is the emission I am talking about in 1980 or so. They had this kind of emission. In 1984, they had this thing. And you know what is the emission right now from Mathura refinery? Is about 150 kg per hour. Tremendously controlled, whereas the quantity of the production has increased nearly about 1.5 times to 2 times. Okay. So they have really controlled. They have controlled to the extent that it is nearly about 150 or so. So automatically, if you think that our calculations are correct, so you can almost say, well, it's reduced by 1/4. Okay. Whereas this source will continue to increase, the number of vehicles will increase. You can't stop that. Okay. This thing, people are trying to do something that, okay, supply the CNG, okay, make sure at least there are no more increase in the industrial units coming up. So as a field engineer, as a practical engineer, you have to take decisions, and decisions are based on your modeling work and the experience which you have. And then once you do this thing, then you can find out this thing. The other way, which is even more scientific, is to develop a cost function. Okay. the cost function will be something like cost function for source 1, okay, okay, and times and then that will be cost function depending on the value of q, how much you want to reduce, okay. It will not be a linear function. See, if you want to reduce some emission can be very quickly you can reduce, and certain emission you just cannot reduce. The Mathura refinery cannot have the zero emissions, okay. So plus function, cost function for area source 1 plus cost function for area source 2 plus cost function for national highway. That may even include realigning the highway, okay, okay, and then you can want to minimize this function, minimize subject to what? Subject to what? Minimize subject to what? Concentration at Taj Mahal is less than, correct? That's what is our objective. That is what we want to do, okay. This also this cost me, so after all national money, right? And you want to plan something for your area, then you develop the cost function. That we are not getting into this thing, that the cost function, you minimize this cost function, okay, subject to that concentration at Taj Mahal is less than 30 microns per liter, okay. This is how we do the things.